Hi, everyone. Let's get started with the session. So we're going to talk about tensors today. The first talk is going to be by José. Unfortunately, Francisco couldn't make it to ASPLOS this year. José received his PhD from Computer Science and Engineering at the University of Murcia in 2012. And as of January 2023, he's a newly minted professor, tenure track associate professor at the University of Murcia. His research is mostly on data orchestration support for computing platforms and more generally on energy efficiency, high performance, intensive communication. And today he's going to talk about Flexagon. So José, take it away.
Thank you very much for the introduction. So I'm going to present Flexagon Accelerator. And this is the outline of the presentation. First, the introduction. So the thing is that since we have been able to implement a very efficient sparse accelerator for DNN processing. So first of all, we need to think about what are the implications against what are the operations that are behind. So here it's the operation of a sparse matrix multiplication that is it's on there. So basically we have two different matrices that need to be multiplied with 0 elements. So this is typically encoded according to different compressed formats, for example, CSR, CSC. Here, in order to simplify the explanation, I'm going to show the matrices like this, without the vectors and indices of a particular compressed data, compressed format representation. And these operations, and look at the dimensions M, K, and N. Later on, I'm going to explain this in detail, because they are important to observe these dimensions and the letters of the dimensions. So the thing is that in order to exploit sparsity in DNN loads, so we need to think about what are the sparsity degrees that happen in modern DNN loads. So we are observing that, and we all know that contemporary DNN workloads from different application domains, computer vision, object recognition, NLPs, etc. So matrices A and B contain sparsity from 0.04 to 90%, which is pretty huge. And these kind of matrices need to be encoded in an efficient way in order to save memory footprint, as I mentioned, using compressed formats, and also to reduce the operations with multiplication by zeros that are completely ineffective, right? So the important thing is that in order to implement this, we need to observe what are the data flows for processing these sparse matrix multiplications. So these data flows basically mean what are the data communication patterns between compute elements and memory elements inside the accelerators. Typically, sparse matrix multiplications can be implemented according to 3 different data flows: inner product, outer product, and Gustafsson. I'm going to show here it's important to understand what are the implications about processing these 3 different data flows. With respect to the inner product, so it all depends on how the different loops in order to implement the sparse matrix multiplications. What are the orders? So according to the letters of the dimensions M, N, and K, in case of inner product, K is the innermost loop, that is the faster dimension. And as we can see here in the figure, the problem here is to identify intersections. That is when the coordinate matches with non-zero elements. As we can see here, just this to give an example, if we are traversing matrix A for a particular row in columns, and then matrix B for a particular column in rows. So we are observing here that this element don't match, that is there is no intersection. But here, in this intersection, you need to implement, we need to multiply, the product operation of these 2 elements, and then do the reductions in order to generate, the output element. So in terms of what are the requirements in doing this, so first, we need to implement some intersection logic in order to identify when this coordinate matches with non-zero elements. Then we need for sure to do accumulation to implement the dot product operations, and we need to traverse matrices A and B consecutively. In terms of the outer product, what happens here is that we are going to traverse matrix A in columns, and then the K dimension is the outermost dimension, as we are showing here in the 3 nested loops. It generates a number of partial matrices according to the K dimension, and then, as we can highlight here, for generating the K partial matrix, what we need to do is to traverse the first column of matrix A in such a way that, in this case, for this non-zero element, we need to traverse the row of the matrix B and then generate for the same m dimension of matrix A, the same n dimension of matrix C, in such a way that we are generating, then we change for K, we are generating the different elements of these partial matrices. So after this stage, we have generated K partial matrices, and then there is an operation which is called the merging. The merging means that we are going to merge these partial matrices in a single output matrix in order to generate the output matrix C. So we are going to do that row by row, and then we need to accumulate the elements that are non-zero in order to produce the output matrix. So what are the requirements here? So we need to implement in an hypothetical accelerator accumulation in order to implement the dot product operations, merging logic, because once the coordinates matches, then we need to accumulate the elements. And in this case, we need to traverse consecutively matrix A and B. Gustafsson, what changes is that the K dimensions is in the middle, and this imposes that we are going to generate independent fibers, what is called fiber, what is independent rows for matrix C, that these partial rows need to be accumulated as it is done with the outer product, but now with a very reduced memory footprint, because they are not partial matrices, complete partial matrices. And then the story is the same. The difference is that in order to multiply each individual element of matrix A, that is the first matrix on the left, with the elements of matrix B, we are going to traverse only those elements that are non-zero from the perspective of matrix B, of matrix A. What happens here, for example, is that we need to jump here from the previous, this element to this other, and their corresponding, row in matrix B. Then we are generating the partial sums for each individual row, and then we need to do, at the end, the merging operation. Okay, in terms of implications are the same as outer product, but in this case, notice the irregular memory accesses of matrix B. So this is, something that we need to take into account, and we precisely consider when we designed the Flexagon architecture, the Flexagon accelerator, that in a single hardware substrate is able to implement the 3 data flows, and actually there are 6 data flows because M and N can be interchanged. So as motivation, contemporary SPM accelerators are just tailored for one specific data flow. For example, we can see here in the table, Sigmax, Tensor, for example, are prepared for inner product, Matrato and Gamba for Gustafsson, and Space and Spark for outer product. And these are the architectural features that are necessary in order to do that. Flexagon, as I'm going to introduce, I'm going to explain later, the design is able, with a single hardware substrate, is able to implement the 3 data flows efficiently. So our motivation was that, okay, take a look at the sparsity degrees for each individual DNN layer, for each individual DNN model, and see if a single data flow is the best suited for all of them. And we observed that, as we are showing here in this figure, that these are the layers in the xi dimension, these are the different DNN models. And as we can see, the optimal data flow changes not only depending on the DNN type, but also depending on the layer inside DNN type. So these 2 that are here at the bottom are NLP models. That seems to be the trend is to using Gustafsson in a more, that is the best treated data flow is Gustafsson, while others is a mixture of them. So based on that, we thought, okay, why don't we design a single accelerator that can fulfill all these? And we can program the accelerator in such a way that they can, for certain layers, they can go with inner product, others with outer product, depending, on the best decision. So that's the motivation of implementing Flexagon. Flexagon, the design, I'm not going to go into the details because of lack of time. Later on in the poster session, we can discuss more and offline more. So the idea is that it is implemented according to the design philosophy of flexible accelerators, and I recommend, if you didn't take a look at the Stone tutorial that I presented with other colleagues from Georgia Tech Sunday. It is composed of distribution network, that is here in color, the multiplier network in blue color, and then the reduction network. Now we need to incorporate the merging network as well. But in case of Flexagon, what happens is that the distribution network, we need to distribute the element input and weights into the multipliers to make them stationary, for example, according to matrix A. After that, the multipliers do the multiplications, and then you need to reduce the dot product and do the merging operation. So we have invented for the first time a unified merging reduction network, because other accelerators just has two different network on chips for merging and reduction. We have defined that. This is a detailed view of that. And for each individual, the magic here is that for each individual node of this network, we have the possibility of having it configured as a comparator in order to do the merging operation, that is how to the coordinate matches and detect that, or do the reduction, the conventional reduction. So what is this other? That's why we have the other here. And then we have the multiplier also with the possibility of forwarding, because we need to first reduce, store the reduction, and I'm going to explain where. And then after that reduction operation, we need to fetch again the data in order to do the merging operation. Remember the other product and Gustafsson data flows that I explained earlier. So in order to store the elements, so we have invented a new L1 customized on-chip memory organization composed of three different memory structure, on-chip memory structure, according to the necessity and requirements for matrix A, B, and the partial sums in order to compute matrix C. So for the stationary phase, that is for storing the elements of matrix A, since the access are consecutively, as I explained earlier, so we have implemented this FIFO in order to send the data to the corresponding multipliers here, because this is here in this place, so we are sending the data to the multipliers stationary. Then for matrix B, in cases of inner product and outer product, accesses are consecutive, but in terms of Gustafsson, that is not the case. So that's why we have implemented here a low cache in order to capture this irregularity in the memory access patterns, in the accesses. And finally, in order to store the partial sums, we have implemented this APS-RAM with a specialized structure in order to store the partial sums, the partial matrices, the partial rows or fibers, and then fetch them again in order to do the merging operations. So as experimental methodology, we have compared Flexagon against state-of-the-art accelerators, sigma, inner product, spark, outer product, and gamma for Gustafsson. And we have configured and implemented and evaluated this accelerator using SST Stone, that is Stone tutorial, as we presented on Sunday. And we have, for a fair comparison, we have used the same parameters for all of them in terms of number of multipliers and others, etc. We have carried out, in the paper you will get more details, end-to-end evaluation that is run complete DNN models, the ones that are here, I presented earlier. For a more in-depth description and analysis, we have selected different layers from the different DNN models, according to this. These are the configurations. And then we have provided RTL evaluation, that is using these characteristics. Results. So sparse accelerators are much more efficient than CPUs and GPUs in order to process SPMs. So we have normalized all the execution results here, speed ups with respect to MKL. These are the accelerators. And then we have compared, what is the speed up. As we can observe here, average speed ups are tremendous when we are comparing, against state-of-the-art accelerators such as sigma, spark, and gamma. With respect to area and power results, for sure, we need to add this specialized L1 memory on chip organization. We have to also add some lightweight complexity to the merging reduction network. We have some overhead in area and power, as we are showing here. But if we consider just overall, performance per area or performance per watt, here is performance per area, so we are observing that our accelerator is much, much better as compared to sigma, spark, and gamma. So just to finalize, contemporary fixed data flow accelerators cannot adapt well to the particularities of modern DNN workloads. That's why we have implemented this Flexagon that is able to implement the 3 data flows with 2 versions each, that is 6 data flows overall. And finally, we're observing that in terms of performance per area, just one particular metric, the benefits are tremendous. So thank you very much for your attention, and just please, questions, I will be here for answering them.